In this video, we're going to put together interaction diagrams, free body diagrams, and Newton's first law to show you how to draw vector addition diagrams. So I've got over here a situation. We've got 3 books stacked on a table, and then I've already got the vector, the free body and the interaction diagrams drawn out here. If you're not sure how to do these 2 diagrams, you first need to hop over to my other video, and I'll link that up in the corner. So we've got the free body diagram, and before we jump to the vector addition, we first need to look at what's happening with the velocity and then use that to determine what happens with the forces. So looking at this picture here, we're looking at the forces on the green book, and the velocity here is constant. Okay. Now it's a constant of 0. It's not moving, so its velocity stays at 0. But more importantly, it is a constant velocity. So Newton's first law tells us that if the velocity is constant, then the forces have to be balanced. And so this idea of balanced or unbalanced is going to become the restraint on our vector addition diagram that tells us exactly how it needs to look when we're done. So with vector addition, what we're going to do is redraw each of the vectors from the free body diagram, but we're going to draw them according to some specific rules. The first thing we're going to do is we're going to redraw the FG vector. Now, you don't have to always redraw FG first, but 99% of the time, it's going to turn out easier if you do it that way. And so I will redraw FG right here. Okay. And so to add vectors together, which sounds a little weird, how do we add arrows? But to add vectors together, what we are going to be using is called head to tail construction. So head to tail. And so when we talk about the head of a vector, what we mean is the pointy end. So these are the heads of each of these vectors. And when we talk about the tail of a vector, we mean this right here, the not pointy end. And so what we're going to do is we're going to, starting at the head of our FG vector, I'm going to start drawing the vector for the normal force from the blue book. So I will take my pen, I'm going to put it at the head of FG, and I'm going to draw, my F in blue. Okay. And notice that it points in the same direction as it does over here in the free body diagram. That's another rule, like we can't just draw it pointing in a different direction. So I've done my FG, I've done the normal force from the blue book, and now I need to do the normal force from the red book. So according to the rules that I just talked about, I would need to start right here, but that's going to cause me to overlap onto another vector, and it's going to look a little messy. So I'm gonna hop over here to the side and start right there. Now this is where the balanced unbalanced comes in, because I really have 3 choices. I could make F in red, I can make it end here, I can make it end at some point before FG, or I can make it end at some point after. And the reason I know, or the way that I tell which one is which, is that I have to look over here to the balanced unbalanced. So I've already decided that the forces are balanced because the velocity is constant. So that means that when I draw my Fn red vector, that I have to end right there. So I will draw that, label it Fn red, and I've drawn my last vector. And so one of the other rules for vector addition is that balanced forces means that you end where you began. Okay. And what I can get from this diagram here is that if I were to look at the magnitudes or the number of newtons of each force, I would see that the normal force from the red book is equal to the sum of the weight and the normal force from the blue book. Now their signs would be opposite. I'd have some negatives thrown around, but if I look at it just from a magnitude perspective, the number of newtons, adding these up here will give me the red vector. Now let's do one other example where we don't have just up and down forces. So in this situation, we've got a box being pulled by a rope along a rough floor. Okay, the rough floor is going to be key there, and it's being pulled at a constant velocity. So we already know that the velocity is constant. The problem tells us that, and that means that the forces have to be balanced, and that is what Newton's first law says. Constant velocity means balanced forces. Now, if I look over here at my free body diagram, notice that I've got a normal force from the floor. Okay. I've also got the floor causing a kinetic friction force. And then the rope has some tension, and the earth pulls on the box through gravity. So now I'm going to, like last time, redraw all of my forces one at a time, sticking to that head to tail construction. Now I'll start here with FG. Okay, and now I can redraw. Vectors are like numbers. You can add them in any order that you want, and mathematically it doesn't really matter. But because we're drawing a picture here, it's sometimes easier to draw them in certain orders as opposed to others. And so, in my opinion, the easiest way to do this is to draw them so that you get a shape, like a square, or rectangle, trapezoid, some kind of closed shape. So if I know that my forces are balanced, so I have to end my diagram right here. So if I want to make a shape, my easiest bet is going to be to draw one of my sideways forces. Now I could draw my kinetic friction force and go that way, but I'm going to run into my interaction diagram up here. So instead I'm going to draw the tension force, okay, because I've got more room over here. Okay, so there's tension. And then I could draw my kinetic friction here, but again, that's not going to make a shape that I'm familiar with. So while it's valid mathematically, I'm going to choose to draw my normal force next. And so this is, again, where balanced unbalanced comes into play. I have to make the normal force equal to gravitational force, because if I went higher than that, if I drew it all the way up here, then when I draw my friction force, I have to draw it the same direction, and so I'm going to have a gap here. So I can't make my normal force longer than Fg, and vice versa, I can't make the normal force shorter than Fg for the same reason. When I draw my kinetic friction, I'm going to get a gap here, and that would not show balanced forces. So the only way to draw the normal force is to make it exactly as tall as Fg. And so now I've got to draw my kinetic friction force, and I've got all four of my forces. And so from this diagram, I can use what I know about geometry to go ahead and start figuring out some relationships. So I know that the tension force has to be equal to the kinetic friction. And that's because this is a rectangle and the opposite lengths of rectangles are equal. And I can say the same thing about the normal force and the weight. Now I have drawn this as a square looking thing, but I can't assume that it's a square. Okay, I don't know if Fg and Ft are equal, even though I've drawn it as a square, so you have to be careful about that. But I do know that it is at least a rectangle. There's no way to draw a shape like this so that it looks anything like a rectangle. That's the only thing I've got. So I do know that Fg and Fn are equal and that the kinetic friction and tension are equal. So that's it for vector addition diagrams for balanced forces. The key here is always to start with the velocity and then use that to infer whether or not the forces are balanced or unbalanced. And if it's balanced, you have to end your diagram where you began. Now when we get to unbalanced forces, it gets a little different, but the process is still the same. Figure out your velocity, determine that they're balanced or unbalanced, and use that to help figure out what your diagram should look like.